about 26 million years ago, they uplifted and deformed the overlying rock strata and also altered the overlying topography. Of course, this is just one example of crustal magnetism, but various researchers have also recognized this idea of a transcrustal magmatic system in which we have these tiers of crystal mush and high temperature regions throughout the entire crustal column, ultimately feeding a edifice or cluster of edifices on the surface. However, how this kind of system leaves a signature or a fingerprint on the surface still remains relatively unexplored. So looking at this kind of relationship is really the main goal of my research. So for this talk, I'm going to break down the three main questions. First, how does crustal magnetism relate to the surface? Secondly, what is the topographic consequence of transcrustal magma emplacement? And finally, what is the impact of crustal magnetism on long-term landscape evolution? And to answer these questions, I'm going to break my talk down into two main sections based on two of my projects. The first is a data-driven study that we published just last year in Geology, titled Time-Evolving Surface and Subsurface Signatures of Quaternary Volcanism in the Cascades Arc. And for this, we determined new estimates of edifice volumes. We also analyzed the relationship between surface volcanism and crustal structure using a variety of geophysical data sets. And then finally, we explored surface and subsurface relationships throughout the Quaternary. In the second part of my talk, I'm going to show a more model-based study that we just submitted to JVGR earlier this month, titled Development of Magmatic Topography Through Repeated Stochastic Intrusions. And for this, we expanded a single intrusion elastic deformation model to regional scales in order to constrain the effects of stochastically emplaced intrusions on topography. We also parameterized surface displacements from these intrusions as a thin elastic plate. And then finally, we attempted to quantify long-term landscape response to intrusions within select volcanic environments. So to dig right in, decades of work within the Cascades really make this area a great location to analyze the relationship between volcanoes at the surface and the underlying magma transport network. Besides geology-based studies, researchers have also analyzed the structure of the crust under the Cascades using a variety of regional geophysical data sets. And these include things such as isostatic residual gravity, where here negative anomaly values are associated with less dense crustal material. Also surface heat flux related to advective and conductive heat transport within the crust, as well as GPS-derived strain and rotation rates, which constrain interseismic surface motions. And finally, seismic tomography, shown here as 10-second and 15-second surface wave phase velocities, which constrain the convolution between rock composition, temperature, and fluid content within the shallow to mid crust. Recently, our colleague Dave Ramsey at the USGS has compiled a database of all known volcanic vents in the US portion of the Cascades that have erupted throughout the Quaternary. And here I'm just showing them as a series of black dots in map view. In total, there's about 3,000 entries. And for each entry, we have the location of the vent, the morphologic classification of the edifice associated with that vent, and also the epoch age of the last eruption for that vent, broken down into Holocene as well as late, middle, and early Pleistocene. So the main goal of this project is to combine this vent database with the previously published geophysical data to analyze the relationship between the surface and the subsurface. And to do that, we first determine edifice boundaries from topography. We then use these boundaries to generate arc-scale edifice volume estimates. Afterwards, we analyze the correlation between edifice volume, volcanic vents, and regional geophysical data. And then finally, we quantify the temporal distribution of volcanism in the Cascades. So to determine the boundaries and volumes of edifices from topography, we generated a semi-autonomous procedure that expands on previously published edifice identification algorithms. And I'm not going to go through the entire procedure, but to give an example, I'm showing here the Sisters Volcano Complex in Central Oregon, where here all the red triangles are the vents from our database. For those who aren't familiar with this region, the Sisters is a group of four main stratovolcanoes, that being North Mill and South Sister, as well as Broken Top to the east, and a smaller stratovolcano called Mount Bachelor to the south. So to try to find edifices from topography, we first postulate that the highest slope areas are associated most with volcanic edifices. And thus we determine regions that have a slope value that's greater than some threshold value. And that's what I'm showing here as these yellow pixels. And what I hope everyone can see is that we wind up with these circular clusters of high slope regions that ultimately correspond to our edifices. From here, we automatically determine each circular cluster and then cut the topography out around that cluster, and then analyze it using a previously published edifice identification algorithm called the Modified Basal Outlining Algorithm, or MBOA, to automatically determine a edifice boundary from topography. So here's the main result for the Sisters region, where the black lines are all determined edifice boundaries. From here, we calculate volume by integrating topography within all bounded regions. Doing this for the entire Cascades, we determine edifice volumes and edifice boundaries and associated volumes with approximately 2,400 edifices throughout the arc. And here I'm just showing the along arc distribution of both the number of vents and associated edifice volumes broken down by edifice morphologic type. Not too surprising, some of our greatest volume regions are associated most with the main magmatic centers of the Cascades, including Mount Shasta and Medicine Lake, Sisters and Newberry, as well as Mount Adams, Mount St. Helens, and Mount Rainier. Cumulatively, we determine a total edifice volume of approximately 2,700 cubic kilometers. And what's interesting is if we compare that to the total extruded volume estimates from Hildreth 2007, which incorporate both the US and Canadian portions of the Cascades, of about 6,400 cubic kilometers, we find that edifices account for approximately 50% of total arc extruded volumes. And we aren't the only ones to find this kind of relationship. In a recent study, Gross and others determined the volumes of monogenic cones in South America and compared it to the volumes of their associated lava flows, and also found this kind of one-to-one ratio. So this is a pretty cool result because it suggests that we can get rough estimates for an arc's extruded volume based purely off of edifice volumes, which can be easily determined from satellite-derived topography. So now that we have these new data sets, shown here as edifice volume per unit area and vent spatial density, we can now combine it with the previously published geophysical data sets to analyze the correspondence between the surface and the subsurface. And we do that through a set of correlation analyses. To start, we first look at only the geophysical data sets and analyze the correlation across each grid. Afterwards, we incorporate our new data and interpolate every grid to the volcanic vents from the database and run a new correlation analysis. So here's the example, for example, is the results for the correlations of just the geophysical gridded data. And to read this graph, the X and the Y axes are the data sets that we analyzed, and the colors within the graph correspond to our correlation coefficients, where warmer colors have a positive correlation and cooler colors have a negative correlation. Also, these X boxes have correlation p-values greater than 0.05 and are thus considered not statistically significant. So overall, what we can see is that there's not many correlations across the gridded geophysical data. And those that do exist, we could have probably easily determined by just looking at each grid. For example, we see this positive correlation between heat flux and elevation, which also corresponds to a negative correlation between heat flux, elevation, and seismic tomography. However, whenever we look at the correlations of the gridded data interpolated to our volcanic vents, we see an overall increase in both the number and magnitudes that exist, with many of those being what we would expect from a magmatic setting. For example, we see this positive correlation again between heat flux and elevation, as well as between heat flux, vent spatial density, and volume per unit area, as well as a negative correlation between heat flux, seismic tomography, and gravity. We also see some correlations that we wouldn't necessarily have expected. For example, when we look at the gridded data sets, we see that rotation rate shares no correlation between it and any of the other grids. However, when we look at the interpolated data, we start seeing a positive correlation between rotation rate, vent spatial density, volume per unit area, and heat flux. And this we kind of interpret as a local magmatic influence on crustal deformation throughout the arc. We can go a little bit further and utilize also the temporal aspects of our database, and thus look at the correlations of the gridded data interpolated to only the monogenic events that erupted during each epoch. For example, this is the results for the data sets interpolated to only the monogenic events that erupted during the Holocene. And if we compare that to those that erupted during only the early Pleistocene, we can see an overall decrease in the correlations. Mind you, the temporal resolution of the database is quite coarse. However, since the geophysical data represents the current states of the crust, we interpret this decrease in correlations as representing a temporal shift within the Cascades, within the crustal magmatic structure of the Cascades throughout the past 2.6 million years. Going a bit further, we also wanted to analyze the spatial distribution of volcanism throughout the arc. And to do that, we first note that our highest number of vents and associated edifice volumes occur at approximately the same latitude within the Cascades, that being around the Mount Shasta and Medicine Lake regions. So in using that, we derived a new metric in which we first normalized our distributions, each distribution, to a 0 to 1 scale, and then simply subtracted the two, generating this value beta, shown here in black. And what beta is it quantifies how distributed volcanism is within a region. So whenever beta is positive, it suggests that volcanic activity is spatially distributed across multiple vents. However, whenever beta is negative, it suggests that volcanism is clustered or focused around fewer vents. Looking at across arc swaths of this, we can see some expected values for beta. For example, we see a trend towards more distributed volcanism around Mount Lassen and the Caribou Volcanic Field, as well as Medicine Lake, the Sisters Volcano Complex, and the Simcoe Volcanic Field. Similarly, we see this trend toward more focused volcanism around Mount Shasta, Glacier Peak, and around the Newberry Shield. And again, we can utilize the temporal aspect of the database to analyze this beta value through time. So this is just an example of that, in which each line here are the various beta values looking at each epoch. And here we've lumped the Holocene and late Pleistocene together. So in doing this, we can see some pretty interesting trends. For example, we see this shift from distributed towards more focused volcanism around Mount Shasta, Mount Baker, and around the Mount St. Helens, Mount Adams, and Mount Rainier area. And a complete analysis of what could be causing this trend was kind of outside the scope of our project, but there's a few processes that could be playing into this. One such process is something that's been recognized by various researchers, that magmatic bodies within the crust can alter the local state of stress within the crust and can deflect magma transport towards the body, which could also then translate to the surface. Conversely, we also see this trend from focus towards more distributed volcanism around Mount Lassen and Medicine Lake. And in this kind of regard, a process that could be playing into this is tectonic extension, such as through the impingement of the baseline range onto the eastern side of the Cascades. However, hopefully further work can better quantify why we're seeing these relationships. So just to summarize this project real quick, we estimated a total edifice volume of approximately 2,700 cubic kilometers in the Cascades. Find that corresponds to approximately 50% of total arc extruded volumes. We also see strong correlation magnitudes across multiple data sets whenever we interpolate them to the volcanic vents, suggesting this relationship to crustal magnetism. We also see that data set correlation magnitudes are strongest for the most recently active vents, suggesting a temporal shift in crustal magmatic structure throughout the Quaternary. And finally, we see that the spatial distribution of volcanic activity shows this interaction between evolving magmatic systems and tectonics. So now that we've explored these kind of connections between the surface and the subsurface, we can now go back to some of the main questions of our talk and start examining the topographic consequence of intruding multiple intrusions into the crust within this kind of transcrustal setting. And there's a few locations that this might be quite relevant for, but one I'll point out is Laguna del Mo, where geologic and geophysical evidence suggests that multiple magmatic bodies within the upper crust have driven surface uplift throughout the Holocene. So the main goal of this part of this research project is to analyze the topographic effects of stochastically in place magmatic intrusions on the regional scales, mainly in the absence of erosion. And to do this, we first expand a single intrusion surface deformation model to regional scale crustal magnetism. We then analyze the topographic effects of these stochastically placed intrusions using a variety of metrics. And then finally, we examine the impact intrusions might have on long-term landscape evolution. For simplicity, and just to get the first order topographic effects, we use the elastic deformation model by Fialco and others, which models the surface displacement in response to an inflating penny-shaped crack within the crust. And here I'm just showing the maximum surface displacement using this model for a range of radius and depth parameter space. To expand this to regional scales, we assumed that 2,000 cubic kilometers of magma is injected into the crust as single body intrusions. And thus we determine surface displacements using the inflating penny-shaped crack model during each intrusion's placement. In total, we ran 6 models in which we varied the mean intrusion radius and depth, and then sampled this parameter space using a normal distribution. And real quick, I'm just showing the probability density functions of our intrusion, our sampled intrusion radii and depths for each model. Spatially, we assume that the intrusions follow a Poisson distribution and thus randomly sample our X and Y locations within a periodic spatial grid. Also, I'll say that we start at 0 elevation for our models and then just let the intrusions kind of stack topography as they intrude. So here's the results for these 6 models ordered by the mean radius to depth ratio. To read this, the upper panel shows the topographic relief of our models, whereas the bottom panel shows a cross-section of both the relief and the distribution of intrusions within the crust, with the black dashed line being the mean intrusion depth. So overall, what we can see is that really it's the intrusion's mean radius to depth ratio that sets the generation of topography. And we can perhaps see that best if we look at the maximum elevation and relief for each model as a function of the cumulative volume of magma that's injected into the crust. And again, as we increase our intrusion's radius to depth ratio, mean intrusion radius to depth ratio, we see increasing amounts of both local relief as well as overall maximum elevations. And another way we can quantify this is by looking at how these intrusions contribute to the overall distribution of topographic volumes. To do that, we first calculate the amount of volume associated with our topographic relief. as well as the volume going from 0 to our minimum elevations. We then simply divide these two values, creating this metric zeta, which, and what zeta tells us is whenever it's less than 1, it suggests that the intrusions contribute mainly to regional scale crustal thickening. And whenever zeta is greater than 1, it suggests the intrusions contribute mainly to local topographic generation. So looking at these zeta values for all of our models, we can see that for each model, zeta is always less than 1, suggesting in this case that our intrusions are contributing mainly to regional scale crustal thickening. However, we also see this near linear relationship between the mean model intrusion radius to depth ratio and our zeta. So as we, again, increase our intrusion radius to depth ratio, these intrusions start contributing more and more towards local relief. Another analysis we wanted to do for these models was analyze how well we can parameterize the topographic response of these intrusions as the response of a thin elastic plate to a set of forces at the plate's base, if we assume that the intrusions occur at the same depth. And to do this, we take the Fourier transform of the thin elastic plate equation, and thus derive this function phi, which is the isostatic response function of the plate to a set of forces within the spectral domain. So here, G is gravity, and rho m is an assumed density of magma. K is our spatial wave number, and D is the flexural rigidity of the plate, which depends on the plate's thickness. So for this, we tried to find the best fitting effective elastic plate thickness that can recreate the topographic response. And to do that, we simply find the minimum error between our isostatic response function, given a assumed elastic thickness, and the transfer function or emittance between our intrusion thicknesses and topography. So here's the results of this analysis, in which the black dots are the intrusion thickness to topography admittance, and the red line is our best fitting isostatic response function. For all models, the best fitting effective elastic plate thickness was always thinner than the overall depth of our intrusions. However, we can see that overall, the thin plate does a pretty good job of characterizing topographic response. Near or around the 100-meter scale wavelengths, we see that the emittance and isostatic response functions are nearly identical. They begin to diverge around the kilometer scale, but come back together around the flexural wavelength of the isostatic response function. And for those who might not know it, the flexural wavelength is the wavelength at which the plate the plate compensates all loads at depth. And it's given by this equation here. So again, depending on a gravity, density of magma, and a flexural rigidity. Of course, intrusions don't necessarily need to follow just a Poisson spatial distribution. And thus, we also tested the effects of a Gaussian distribution on model topography. For this, we ran another set of 6 models where we kept the same radius and depth sampling parameter space. But here we assume that the intrusions in place around the center of our grid, following this Gaussian spatial distribution. So here are the results for this model. And here I'm only showing 3 of the models, but what we can see is that the created topography is vastly different from what we had before. Rather than regional scale crustal thickening and overall uplift of the surface, instead these intrusions generate a near axis symmetric landform in which the relief of this landform is mainly controlled by the mean depth of our intrusions. And although I'm not showing them here, the zeta values for these models are always greater than 1. So it just kind of also suggests this trend towards local topographic relief. So what can these two models tell us about how the landscape or how topography responds to crustal scale intrusions? Well, what we're seeing is that although a single intrusion's radius and depth parameter uh, might contribute to the maximum displacement that occurs during each individual emplacement, it's really the spatial distribution of these intrusions that drive or control overall topography. Whenever intrusions are spatially dispersed, we see this quasi-uniform uplift over the entire region associated with crustal thickening. Whereas whenever intrusions are focused and overlap within the crust, we see this generation of a single landform, contributing mainly to local topographic relief. So now that we have this kind of intuition about how the surface is uplifted by this kind of crustal scale magmatic structure, what I want to do in the last part of my talk is give a small discussion about how we can start thinking about the long-term landscape response to crustal scale magmatism. And to do that, we first need to build a bit of a framework for understanding, or a simplified framework for understanding landscape response. I'm not going to go through the entire research project, but in a previous publication that I did with Leif Karlstrom and Josh Roaring at the University of Oregon, we analyzed the erosional response of the landscape to a single uplift perturbation, such as what one would see from a lacklith or another shallow intrusive body. And what we found was that the overall landscape response can be characterized by two main non-dimensional values. The first value, beta, compares the relief of the perturbation to the local topographic relief. And the second value, eta, compares the size of the perturbation to the wavelength of surrounding topography. And with these two numbers, we found that the landscape can respond in three main ways. Whenever beta is small, mainly less than 1, the perturbation generates very little disruption within the landscape, and ultimately just creates a small concavity that erodes away. And also for these, I'm just showing profiles of landscape response through time. Whenever beta is greater than 1, but eta remains small, the perturbation generates non-permanent landscape transients. So in this regard, the perturbation cuts off the upstream river channel, generating an internally drained basin that then dissects and erodes through the perturbation. However, whenever beta and eta are both large, the perturbation becomes the dominant landform. It becomes the main drainage divide of the landscape and causes regional scale basin reorganization. So given this framework, we attempted to quantify or suggest an expectation for how select volcanic regions might evolve through time based on their intrusive signature. For example, the current uplift of South Sister in Central Oregon, as well as the Socorro magma body in New Mexico, have generated relief on the meter scale, which is vastly smaller than the surrounding topography. And thus, in this regard, these two locations could be considered a regime 1 response, where we have this local disruption with no permanent landscape change. Conversely, the Pleistocene to present construction of Unturuncu and Azufre in Bolivia and Argentina have generated kilometer scale relief, which is quite larger than the surrounding environments. And thus it could represent, these landforms could be regime 3 responses, in which we have this regional disruption and permanent drainage reorganization. The Henry Mountains, of course, are also a clear example of a regime 3 response, as they appear to have been a dominant landform on the Colorado Plateau since their formation around 25 million years ago. So through this, we have these clear examples of regime 1 and regime 3. However, regime 2 is a bit more difficult to quantify, as it really represents the transient stage between short-term volcanic deformation and long-term landform generation. However, we think we see two locations that fall within kind of the middle ground. For example, during the 2011 eruption at Cordon Cool, a shallow lacklith or magma body generated approximately 200 meters of uplift over a 30-day period. And in this regard, the scale of that uplift was comparable to the main edifice that erupted. Similarly, Laguna del Mo, as I discussed previously, has these multiple magmatic intrusions within the upper crust that has led to tens of meter scale uplift within the region, which is comparable to the surrounding topography. And thus we quantify these two locations to be in this middle ground between regime 1, 2, and 3. And what I will say is that, this isn't a very extensive analysis, but mainly we mainly give it to give this kind of open discussion to start bridging the gap between geomorphology and volcanology and start thinking about how these how these crustal magmatic systems might be impacting the long-term landscape response going forward. So just to finish up, as a quick synopsis, throughout this presentation, I explored the relationship between surface topography and the underlying crustal magmatic system. In the first part of the talk, we used a data-driven study in the Cascades to first determine edifice volumes throughout the arc, and then compare volcanic vents to regional geophysical data sets to analyze the relationships between the surface and the subsurface. For the second part of the talk, I showed more of a model-based study in which we expanded a single intrusion model to regional scale magnetism to analyze the topographic response to multiple intrusions within the crust. And we also started exploring what we would expect to be the landscape response to magnetism in select volcanic settings. And with that, I'll end it here and say thank you.
Thank you, Dan. Thanks for the great talk. We have time for questions and discussion. Please go ahead and you can just raise your hand or put it in the chat. Looks like we have a question from, well, several questions, looks like. We'll start with Hannah Buckland. Hannah, I'm going to read this, but if you want to jump in, that's fine too. Okay, it's a question related to part 1 of the talk, and sorry if she says she's sorry if you missed some of this, but do you account for missing edifice volumes, for example, from caldera collapse? And could you comment on how significant the absence of these volumes might be?
Okay. No, we didn't. Well, actually, let me rephrase that. There's really only 2 main calderas, I believe, in the Cascades, that being Newberry and Crater Lake. And in regards to Newberry, we did not account for the missing volume from that caldera. However, I will say, despite that, Newberry still was one of our largest volume edifices. In terms of Crater Lake or Mount Mazama, we supplemented that missing volume with geology-based estimates for what Mount Mazama was before its eruption.
Sounds good. And also I should note that if you would like to speak, you definitely can. What I'm going to do is going to alternate between the chat questions and the raise a hand questions. So Bill Burton, you can give a question if you like. Just go ahead and unmute yourself.
Thanks for the interesting talk, Dan. I was wondering in general how your work builds on that of the Hildreth professional paper, or adds to it, or maybe differs from in terms of, building the whole Cascade Arc edifice. What have you found that adds new insights to that, kind of in words?
Yeah, I would say one of the biggest things was, we were able to determine these volumes for a lot of various edifices. And of course, Hildreth looked at edifice volumes, but he mainly focused, I believe, on the main stratovolcanoes of the Cascades. Whereas through our algorithm, we incorporated both monogenetic and polygenetic edifices. So, and I don't recall in the report whether he made a connection to the geophysical data in the Cascades. So that would also be an extra contribution.
Yeah, his main point that I recall was that the vast volume, of course, was actually basaltic shield volcanism. And that really defined the axis of the arc more than the relatively late stratocones.
Right. Sorry, could you say that once more?
I was just saying his main takeaway, I thought, was the fact that the 90% of the volume or whatever was created by shield volcanism, basalt volcanism, and that was a better indicator of the actual axis of the arc than the alignment of stratovolcanoes.
Oh, that's a good point. We didn't really, yeah, I guess we didn't look too much at kind of these arc axes. And in fact, we contemplated a lot whether Newberry is considered Cascades or if it's kind of off arc in that regard. So we kind of skirted away from that kind of discussion. But you are right. This was one aspect of the database we didn't characterize, was kind of these eruptive deposits, actually, that I believe Hildreth did incorporate within his estimates.
Thank you.
Mhm.
All right, next we're going to go to Sam's question in the chat. And Sam asks, in your elastic thin plate simulations, what do you think the effect is on real-world non-elastic deformation processes above intrusions you study? You mentioned the Henry Mountains, for example, where porosity reductions, that is volume loss, have been shown to occur in bent host rocks. Would such processes just affect the magnitude of your resulting values, uplift volume, or reverse trends you obtain now using linear elasticity? And that question's in chat too, if you want to take a quick look at it, Dan.
Yeah, I might look at that one.
I guess the first thing you could start commenting on is your elastic thin plate simulations. What do you think is the effect of real-world non-elastic deformation processes?
Right, that's a good question. We did, one thing I will say is we kind of ignored the viscoelastic component in order to really just look at the first order trends and to try to quantify it in a simple manner to start out with. I think going forward, it would be great to start incorporating kind of a viscoelastic component, especially as it'd be expected that the temperature field changes throughout the crust as we intrude so much magma. And in that regard, I think in terms of the initial models, we would probably still see an elastic response, at least at first. But as as the crust starts warming up, we would start seeing this transient viscoelastic relaxation within the crust. So we probably wouldn't be getting nearly as much topographic relief or crustal thickening that we see in the models. But it's also it would also be that kind of time variant process that we'd have to account for.
Yeah, and then Sam's kind of second part question here of the question here is specific to porosity reduction, and he refers to the Henry Mountains, but he also goes into says Henry Mountains have been shown to occur in bent host rocks. Would such processes just affect the magnitude of your resulting values or reverse trends you obtain, using linear elasticity?
I'll be honest in that regard. I haven't looked too much into porosity reduction, so I'm not sure how well I would be able to reply to that.
Yeah, and all these things, if you folks want to follow up, please go ahead and do that. Okay, we've got a few more chat questions already in the queue here. Jonathan Delf writes, could you use the regime plot to inversely calculate properties of the magmatic intrusions? That is prop depth, depth of intrusion rate, for example. It seems like it would be a useful trade-off plot to compare with seismic data.
By regime plot, Jonathan, you mean the plot I showed at the very end, just to verify?
Yeah, the plot you showed at the very end. Yeah, that one.
Okay.
Yeah, the one that your mouse is in. Yeah, perfect.
Oh yeah, sorry. I thought I clicked on it. I'm not entirely sure. One aspect to consider for this is, of course, we're looking at only that intrusive volume, but there's also an extrusive component that could easily be playing into this regime 1, 2, and 3 response that we didn't characterize in this simplified model. And I think if you could separate the extrusive from the intrusive, then perhaps you would be able to to get the properties of magma out from that.
All right, cool. Thank you.
Sure.
All right, and Shao writes, how can climate, for example, deglaciation or glacial coverage change and erosion rate, for example, factor into the landscape response model, especially when going further back in time?
Yeah, trying to think the best way to frame this. So, sorry, where was that question at?
Yeah, just at the end of the, so I think the major question really has to do with, if you include glaciation, deglaciation, how will it, as you go further back in time, how does that influence the result of your, or could it result in your calculations or your interpretation of your calculations?
Right. Well, it would be a very different process compared to what we modeled. Of course, we looked at kind of this fluvial regime in that regard, as opposed to glaciation. So I would expect it would be altering the state of stress of the crust, which, if we think about that in terms of a magmatic model, it could, of course, generate some variability in terms of the topography that we see. And in terms of the erosive aspect, looking at, say, like the Cascades compared to other volcanoes, the Cascades are highly eroded compared to other locations. So I imagine we would have to requantify or reframe kind of what we would expect the landscape response to be if we incorporated glaciation and deglaciation with that.
I guess while other folks are maybe formulating a last question or two, I had a question, Dan. And so you go through the process. I think is really intriguing, looking at extrusion rates and looking at edifice size as it's one way of getting at total extrusion rates. And then, of course, just depending on the beta factor, they'll get at the how much the intrusion influences topography. But I was wondering if you could comment on kind of the combination of the two, intrusive extrusive ratios, and how much you feel like this work could be extended to try to get at these values.
Yeah. So yeah, I think throughout this Cascades work, it was mainly kind of the extrusive components, mainly the edifice component, of course, that we keyed in on. But one aspect is I think there's no doubt an intrusive components, and I think through the second part of the project, kind of the main goal was to try to see what would the topographic response be to these intrusions in order to try to characterize it in the Cascades. I think it's a bit difficult to have some expectation for how intrusive magnetism is altering the topography, as we have not only edifices, but these large lava flows that have covered a lot of the portions of the Cascades, and those carry with them their own kind of processes and erosive responses. So going forward, part of the main goal in the second part of the project was, or part of the talk, was to start thinking about how we could quantify this topographic signature. Quantify this intrusive signature on topography. I'm not sure if that quite answered it or not.
Yeah, well, I think it's a very hard question to answer. I just wondered if you could get at the ratio, constrain the ratios of it, of the extrusive to intrusive. It's sort of classically quoted, but very imprecise sort of values.
Yeah, and actually, these values vary quite a lot. I know they go from 2 to 100 times difference.
Yeah.
So I think, obviously, geophysics is a great way to try to quantify at least the active or the density, the regions in the crust that have a density difference or some fluid content in it. But I think topography could be developed as another tool to try to quantify that.
Excellent. Other questions? Well, what we can do, invite all of you, if you can stick around a little bit longer, and if you'd like to talk to Dan a little bit more individually, we'll have a little bit of a smaller session here, but for the folks that need to leave, feel free to go ahead and leave now. And thanks again, Dan, for a really excellent talk and several nice pieces of work. We'll all keep an eye out for the paper you have that's submitted, and hopefully everyone take a look at the other papers Dan has presented here today. Thanks again, Dan.
Yeah, thank you.